GCSEs. It all works towards that. It's chapter 2 in the physics caboodle textbook, or science trilogy textbook. It's useful for year 7s too. Now, some of the stuff we're doing today, we're looking at infrared radiation. Now, it's actually, if you look at the caboodle textbook, it does say physics only, but it is useful for you to know anyway, because some of you will be going on to doing separates, and you might not have a chance to do this again. So, it's not difficult to get your heads around, so we'll have a look at that. So infrared radiation, what is infrared radiation and what does it do? But before we start, we've got a recall quiz, high five. What is our formula? Work done equals GPE equals KE equals efficiency equals and power equals. Okay, so pause the video, have a go at answering those. If you've got those, if you've done it and you've unpaused, we'll go through the answers now. Right, remember work done is force times distance, which is Fs. GPE equals mgh, mass times gravitational field strength times the height. KE is kinetic energy, is half mv squared, which is mass times velocity squared. Efficiency is the useful energy divided by the total energy input times 100%. And power equals energy divided by time. And if you rearrange that, energy is power times time. P equals E over T. So hopefully you got all 5 correct. You'll get a virtual high five from me at the end of the video. And remember, you can't buy those in the shop. So what we're focusing on today, infrared. What is infrared? Well, infrared, your light that's coming around you right now from the sun, from the lights around you, is what we know as white light. Now, Isaac Newton is famous for his work on laws of on forces. However, he did do lots of work on light as well. What he discovered is that white light is actually a mixture of 7 colours. We call those 7 colours a spectra or a spectrum. Okay, so that spectrum is the 7 colours, or we get 7 colours of the rainbow. So white light is actually, if it goes through a prism, glass prism, it will split. And that's why we get rainbows, because if you imagine rain falling and light travelling through from the sun, it disperses the light. This is called dispersion. And what you'll see is you've got the 7 colours of the rainbow. Richard of York gave battle in vain. Red, orange, yellow, green, blue, indigo, violet. Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. If I go, this is what we call the visible spectrum. If I go beyond violet, I can't see it anymore. I can see those 7 colours. I can't see beyond violet. Beyond violet will be what we call ultraviolet. And if I go beyond red, so above the red, there's an invisible bit there as well that I can't see. That's called infrared. So again, here's another beam of light going through a prism, and I've got a screen there, and I can see my spectrum on that screen. Richard of York gave battle in vain. On that side, beyond the violet, will be ultraviolet that you can't see. And on this side is the infrared. Now you can't see it, it's invisible to your eye. But if I put a thermometer there, you can see the temperature starting to rise. So what is infrared? Infrared is a type of radiation. It's part of the electromagnetic spectrum. It's just like light, but it's an invisible light that you can't see. And what does it do though? It has a heating effect. It heats things up. Every object in the universe, as long as it isn't on 0 degrees Kelvin, which is the same as minus 273 degrees Celsius, if you're not on absolute 0, every object in the universe, if the particles inside of it are moving, have the ability to give out thermal energy, a heating effect by radiation. Okay, so every object will give it out, and you can't see it, it's invisible. It's a heating effect, and we call it infrared radiation. You can't see it, so how do we know it's there? Well, if you use a thermal imaging camera, you can see a little cat there. You can see the certain parts are blue, the certain parts are orange, and certain parts are yellow and green. Well, the brighter the colours, in the red is the hottest part of that cat, and the blue parts are the coolest parts of that cat. So showing you, if you scan it with the thermal imaging cameras, you can see, that's how we use these thermal imaging cameras to see infrared. So you can see beyond bricks, and if there's a collapsed building or something, and there's somebody buried under because of an earthquake, and somebody's still alive, they'll still be giving a heat signature. You might be able to scan to see if there's anybody still living underneath the rubble. Night vision goggles you've got people in like army, soldiers doing that, using it for night vision. You got those thieves who do the car chases, and they get the police on the helicopters trying to chase somebody, and they run out of the car because they're starting to run into the fields thinking it's dark, they can't get seen. But the helicopter's got thermal imaging cameras, and they can see this little guy running as fast as he can like an idiot through the field. Okay, I'm trying to hide in the trees. So, radiation then. So infrared radiation, what does it do? Well, this guy's cool and this guy's hot. Why is he so hot and why is he so cool? Well, it's something to do with the colour of the t-shirts that they're wearing. He's wearing white, he's cool. He's wearing black, he's hot. Why? Because white is a reflector. White reflects the infrared radiation. Black absorbs that infrared radiation, absorbing more of that heat. Okay, so some examples then. We just talked about it. Thermal imaging camera there. Okay, you can see it's cold-blooded there. The scorpion there, it's cold compared to the surroundings is very, very hot. That's somebody in the background there. You can see it's cold-blooded. There's your cat again. There's your night vision. Okay, you can see somebody in the building. And okay, now the practical. There's a required practical that goes with this. There's a couple. Looking at the radiation. So over time, you can measure the temperature either inside a container or the temperature outside the container of how much heat is coming out. There's two ways of doing it. But what you're going to do is make sure that these bottles or these cans are exactly the same. So you usually have a black, a silver, sometimes a clear one, or we have a white one. Okay? And then sometimes you can have a black shiny and a matte black. Now what do I mean by matte black? Matte is when it's like a dusty black. Shiny black is when it's got a sheen, a gleam to it. Okay? Then you've got matte silver and shiny silver, like a polished silver. And then you've got either matte white or shiny white, or you can have a clear one. And you can measure the temperature over time. Now, two little practicals then. So here is a practical here. Do all surfaces emit the same amount of thermal radiation? Okay, so this one is about emission. The other one is talking about measuring the temperature inside the water, inside the can. This is something called a Leslie cube. A Leslie cube is just a metal cube, and different sides are painted different colours. So you've got a white side, a black side, and a silver side. So we've got a matte black and a shiny black. We've got a white side, which is this one there, and we've got a silver side. So let's click on it. This little thermometer is on the white. So I'll click on that. It was already on the white. And then let's press start. And I'm going to put some hot water in there. And I'm measuring the temperature inside and outside. So on the outside, I'm getting 32 degrees Celsius. Now let's try it with the silver. Let's try it with silver, we'll get some results here. So with the silver, same thing again. We're going to pour the same amount of boiling water, same volume to make it a valid comparison, same starting temperature of 80 degrees, and now I'm getting 28 degrees. Now we'll do shiny black. Got two blacks, we'll do shiny black. Same again. And we're going to do the last one, 38 there. And we'll do the matte black. So my Leslie cube. I'll start that. Pour my hot water in there. And we'll see what the temperature does. So, matte black then is the winner. So what is that telling us? Well, that's telling us that matte black is the best emitter of infrared radiation. So the most heat energy is transferring out through the matte black. So it's the best emitter, and ironically, weirdly, it's the best absorber as well. So if it's the best at giving out, it's also the best at taking in. So if you imagine I put hot water, your radiators have hot water in them, but what colour is your radiators? Your radiators are usually white. Are radiators the best emitters of radiation? Well, obviously not, because my radiator, white radiator will give about 32 degrees, but a matte black one will give me 10 whole degrees more. So what colour would be the best for a radiator? That's right, matte black would be the best colour. But why aren't our radiators in our houses painted black if that black's the best? Well, that's purely to do with aesthetics. What do I mean by aesthetics? What looks nice? You're not going to want to have your house painted with black radiators unless you're an emo, you're that way inclined, right? So black doesn't really go with most decoration. So white is like a neutral color and looks clean and like bright or what have you, okay? So it's purely aesthetic. It's not the most efficient. Matte black would be the most efficient at emitting. It's the best at giving out, but it's also the best absorber. It takes it in too, okay? So next, these then, do all surfaces absorb the same amount of thermal energy? Well, I'll give you the answer to that. So let's try silver then. Does silver absorb? If I try to heat this up, there's my heater there, and I'm going to try to heat this water up from this radiator there, and I'm getting, after 1 minute, I'm getting 28 degrees. Okay, let's go in order. We'll go matte black next. So you can see I've got a tube, water, same volume of water in each one, and again I'm going to put the radiator on, that heater, same amount of time, same distance to make it a valid comparison. I'm getting 42. I'm going to do white, same practical, and then I will do the last one, which is the shiny black. Now what do you predict these numbers should be before they come up? I'll do the next one. What do you think shiny black will be? What, between which numbers do you think? Okay, so let's have a go. So which is the best absorber of infrared radiation? And again, it's on matte black. So matte black is the best at emitting, which means giving out, emission. It's also the best absorber of infrared radiation, okay? But silver then is the opposite. Silver is the worst emitter and it's the worst absorber. What does silver do? Silver reflects. So next time when you get a takeaway from your local Chinese or your Indian or whichever takeaway you want with a metal tray, so they do come with the plastic ones now, but the metal ones with the white lid on the top, if you look at the inside of the white lid, it's usually silver. The metal tray is silver. Why? Because the radiation, it reflects back in. So it keeps the heat, keeps your takeaway warmer for longer. So next time you go on Just Eat, or what's the other one called, Hungry Horse or House or whatever it is, I don't know. I always use the Just Eat. See what materials the packaging is to keep your takeaway hotter for longer. So white is a good reflector, a poor absorber. That's why in hot countries, they drive white cars. They're all driving white Mercedes, all right? Because white reflects. If it's a black car, it'll absorb. If it's a black building, it'll absorb, and the inside of the house will get red hot. If you live in Spain in the summer, it gets really hot inside. They have blinds to keep the heat out because it gets so hot inside because you need air conditioning. Okay, so in the Mediterranean, you'll see white buildings like that. They'll have flat roofs as well. They don't have roofs like ours because they don't get much rain. So there's no point having pointy roofs to have that rain go off. Good reflectors then will be silver. Silver is a shiny and reflect. So some notes about radiation. What is it? Radiation is the only method of transfers. It can go through a vacuum. Remember, conduction, solids, convection, fluids, liquids and gases. Radiation can go through all of them. It can go through a vacuum. It can come through space. That's how the sun's energy is coming down to Earth, because there's nothing in space. Space is space. It's empty. It's a vacuum. So there's no particles there. So you can't get conduction. You can't get convection from the sun. It's infrared radiation that comes from the sun to the Earth and warms us up. So heat radiation is emitted by any body with a temperature above absolute zero, which is 0 Kelvin or minus 273 degrees Celsius. Heat radiation is a type of electromagnetic radiation, like I said. Like all EM radiation, it travels in straight lines and at the speed of light. That's 300 million meters per second. Bodies that give out heat radiation are known as emitters. Dull black surfaces are the best surface for emitting radiation. Bodies that take in heat radiation are known as absorbers. Dull black surfaces are the best surfaces for absorbing radiation. Shiny white surfaces are very good at reflecting heat radiation. So, how does the Earth warm up? Here's some words. Pause the video. Have a go using those words to see if you can fill those in. Have a go yourself first. Pause the video, or I've sent it on, show my homework on the PowerPoint. Have a go at filling those in. And then if you've unpaused it, we'll have a go at that. You can see there's the sun, and there's the Earth, and there's my planet, Planet Mian, or Planet My Smart Learning, on the other side of the Earth. So radiation is when heat moves around in electromagnetic waves. That's that one there, waves. Like light does. Any hot object will emit heat radiation. The hotter it is, the more radiation it emits. This type of radiation is called infrared radiation, and too much of it will cause sunburn. Okay, you get burned by the infrared. Dark matte colours will absorb and emit the most infrared radiation, and light shiny colours will reflect it. Okay, the main difference with radiation is that conduction and convection could only happen in solids, liquids or gases, whereas radiation will happen through an empty space. This is just as well, as otherwise we wouldn't be able to get any heat from the sun. And this is going to link in, so anything hot emits heat radiation. The hotter it is, the more infrared radiation it emits. This is going to take us on to global warming. Okay, so again, this is physics only and it's taken it to the higher level. And this stuff here is for higher tier students about black body radiation. So the higher the temperature of an object, the more infrared radiation it emits at a given time. So that's obvious. An object that has constant temperature emits radiation across a continuous range of wavelengths. If you've got constant temperature, you have a continuous range of wavelengths. Now, what does it mean by black body radiation? Now, you can see this one here, 750 degrees Celsius. It's more broad, okay? It's more wide, but the intensity is lower. With black body radiation, you'll see that the intensity, so this peak one here is a black body radiation. It's got a higher peak and it's more narrower. Okay, it doesn't go so much on the continuous range like this. So you've got a higher peak. This peak is at one particular point. It's got a narrower wavelength. So it's got a lower wavelength there, whereas this one's got a greater range of wavelengths here. Okay, now, but what do I mean about black body radiation? So an object that is pure black will either continually absorb heat from its surroundings, okay, so that's what it will do. So it's a pure black body, so it will just keep, imagine that was just a black body radiation, it'll either just keep taking in energy, because most things will take in and also give out, but black body radiation will just constantly keep absorbing and not give out on the other side. So imagine something went in this side and came out that side. If it was black body radiation, it'd go in and not come out. So radiation will just constantly keep going into it because it's the best absorber. Okay. On the flip side, it could just keep giving it out as well. Okay. If there's no radiation from the outside of it, if there's pure radiation on the inside of it, it could just continue to just give it out. Now, absorption and emission then. So we're going to relate this back to the Earth, right? So this diagram here. Global warming, as you know, you've probably read and heard lots about it, obviously, in the news and stuff like that, is causing climate change. Now, is global warming a bad thing? Well, climate change is the bad thing. Global warming has to happen. Without the Earth warming up from the sun, it'd be freezing cold on Earth, everything would be ice, there'll be no life on Earth. The Earth's ambient temperature, which is sort of a background rough temperature, is somewhere between 10 and 15 degrees. So that means like the hottest parts of our planet go to about 50 to nearly 60 degrees Celsius, like the hottest deserts like Death Valley in America, or the Sahara deserts type of thing. And the coldest places on our planet go to like minus 50 in Antarctica, when it's really, really freezing. And if you take the average temperature across the world, it's somewhere between 10 and 15 degrees Celsius, which is lukewarm. So it's mild, which means ice would melt and there'd be water. And that allows life to exist on Earth, because life requires water in the liquid form so it can flow from place to place. Okay, so why is global warming a bad thing then? It's because humans are burning too many fossil fuels, and human impact on our climate is that the more carbon dioxide that we keep producing into the atmosphere, because we're burning coal, oil and natural gas, the more infrared radiation is on Earth. Because what happens is the sun's infrared radiation, it comes and hits the Earth, and it bounces back off, it reflects. And some of it though is absorbed and stays on Earth, keeping us warm. Because if you think about freezing cold planets, it'll just hit, like a mirror, it'll hit it and reflect back off, and the planet will be really freezing cold. That's why at night time it gets really cold, because when you're in the Earth's shadow, when you're on the other side. So as the sun's energy comes down, as infrared, it hits the Earth, hits the ground, and it gets absorbed, the infrared gets absorbed. And the rocks get warm, and overnight and later on in the day, that infrared, the heat the thermal energy stored there, the infrared, will radiate back into the environment. And that's why when you get like things like reptiles basking in the sun, like I got a bearded dragon over there, sitting under a basking lamp in the sun, in the desert, in a hot rocky place, whatever, the sun will warm up the rocks, and then you'll see these lizards, they just lie on these rocks because they're absorbing the heat from the rocks because the sun's warmed those rocks up. Okay, so here is what you're getting. So you get absorption of the infrared, and then some of the infrared just bounces and reflects back into space. But what's happening, because carbon dioxide acts as an absorber as well. Carbon dioxide molecules absorb and re-emit infrared radiation back to the ground. So as some of that sun's energy, infrared radiation from the sun, warms the ground up, the ground becomes warm and emits longer wave infrared radiation. What happens is, if you look, the wavelength here is closer together, so there's a shorter wavelength, but as it hits the ground, it gets absorbed and it bounces back up. The wavelength changes, it becomes a longer wavelength. And the longer wavelength, okay, gets absorbed by the carbon dioxide molecules, and that keeps bouncing the carbon dioxide, a bit like a duvet, okay? So if you're lying under a blanket or a quilt and you let one rip, hopefully you don't, it'll stink under the blanket, but it gets trapped underneath, okay? You lift it up for a waft, but that lifting it up, you can't lift up the Earth's atmosphere to get rid of this carbon dioxide or this infrared, okay? It's getting trapped underneath like a bad fart, and it's warming up the Earth's atmosphere. And what's going to happen is our ambient temperature, background temperature, is going to keep rising instead of go above that for 10 to 15, which you might think, oh, that's great, then we'll have nice weather all the time. But as you know, it's causing catastrophic effects around the world. Ice caps melting, which means there's less land for the polar bears to go fishing and get their food. Okay, more water in the oceans, which means there'll be, like we talked about convection current last time, that every time the water evaporates, because the sun makes the clouds, when the water evaporates, you get the water cycle, you get wind with that as well, but you get rainfall, you get more rain, you get flooding everywhere. Now when I was a kid at school, when I was your age, we didn't hardly ever hear about flooding. But in the last year, every year, in the last few years, every year pretty much, or every other year, there's like major floods that keep happening in the UK, in different parts of the UK, and we don't have flood defences on these places. And loads of people are getting their houses flooded with water, and they lose everything they've ever had, and then the insurance company won't pay out and give them money for it. So that's part of the, some evidence towards climate change and global warming. Sea levels are rising, ice caps are melting, devastation for habitats and wildlife. We get storms, you get these massive hurricanes that causes catastrophic damage. And this is just the beginning of it. So what we do as a society and humanity and civilization, we need to reduce our carbon emissions to hopefully slow down the catastrophic effects that's going to affect me, you, your children, my children, our grandchildren, our great-grandkids, and so on and so on. We want them to have a planet still to live on. So, some exam question and key points for you guys. There's 2 there because in your Caboodle textbook it goes through 2 double pages. Now if you look in the physics only book, it's in that one, it does say physics only, but it is useful because it does cross-reference in other sections of your learning, so it's useful to learn, okay? Although it is mostly designed for physics only students. So if you guys are doing separates, that's something you may not have had a chance to cover again, so that's what we're doing in year 9. It's not a year 10 or 11 topic, but you do need to know it for your GCSE final exams. It's also useful for year 7s too. I hope you've learned something at my channel, My Smart Learning. Please like the videos, watch the videos. I'm hoping you're learning stuff and it's been useful for you guys. Please subscribe if you haven't done so already, and share. And I forgot to give you a high five, your virtual high five. Remember, you can't buy these in the shops, so if you got all 5 correct, that's fantastico. And I'll see you next time. Virtual high five from me.